Okay, so the next talk will be Jason Erbele. I'm not sure, sorry. He will tell us about categories in control.
Thank you. So, we'll be talking about categories in control, like I said. And first of all, I want to explain this in terms of a picture. So, in control theory, we have systems that we want to be able to control, and one sort of standard system that we want to be able to do stuff with, to check our work and everything, is the inverted pendulum on a cart. So this is just a diagram that, a schematic diagram of what this looks like. We've got a pendulum that's sitting on a cart. We have a force that we can apply to this cart, so this cart can be moved back and forth. It's only moving in one dimension, so and the pendulum also is only following one dimension. So we can describe this schematic in terms of a signal flow diagram. And this right here is the signal flow diagram that approximately describes this system right here. And so let me describe what's going on a little bit there. Okay, so like I said, control theory, I like to talk about manipulating the system to get it to what we want it to do. So here's the example right there of the inverted pendulum. A more familiar example perhaps is a thermostat. You have the temperature of the room that the thermostat is measuring, and then it controls the air conditioning or the furnace, and then that tells that makes the room hotter or colder, and then measures the temperature of the room again, and you can see the temperature of the room eventually getting to where we want it to be. So that's another example of a control system. So one of the things that is really useful in control theory is the diagrammatic language of signal flow diagrams. And that we can model a system and then communicate that model with these diagrams. So one of the things that's really cool about this is that even though we're only working at the classical level, there are a lot of things that are really similar to stuff that shows up in quantum systems, like the ZX calculus. We've got a lot of similar structures. So there are a couple of features of this signal flow diagram that I want to point out. So we've got these got multiplications that are going on, and we've also got integration. And this integration is basically we're taking a signal that is giving us the force that we're applying to this cart, and then we're adding it to some other signal, and then we're multiplying it, splitting it, and then integrating it over here to get the position of the cart. And then we're doing some more complicated stuff over here that gives us the angle of the pendulum. And so the integration is sort of integral to figuring out where the cart is. And we also have feedback, and so that's what's going on, for instance, right here. We've got a loop that we've got the angle of the pendulum is sort of influencing its future angle. And we also have something like that in the with the thermostat. The control of the thermostat, putting the furnace on or putting on the air conditioning, is going to affect the future state that is going to tell the thermostat what to do next. So with these integrations and with the feedback, what these signal flow diagrams are really encoding is differential equations, systems of differential equations that are linear differential equations, so we're not doing anything too weird. So I guess it's a little bit of a lie to say that this is exactly the signal flow diagram for this inverted pendulum, because we all know that there's a sine of the angle that is going to be showing up here, and that's a nonlinear kind of thing. Anyway, I want to sort of decompose this diagram into its pieces, and that's where the category theory is going to come in. So we've got this category finvect is the finite dimensional vector spaces with linear maps. And we're making it a symmetric monoidal category, not with the usual tensor as the monoidal product, but with direct sum. And we can generate it as symmetric monoidal category with one object, the ambient field K, together with these morphisms. And this morphism right here is actually a family of morphisms that are indexed by elements of our field. Question?
You read them top to bottom?
Yes, I'm reading them from top to bottom. So if you saw Paweł Sowiński's tutorial, he's reading them from sideways, so usually from left to right, sometimes right to left. So if you like his formalism, we're sideways. If you like the quantum formalism, we're upside down. So nobody has figured out a consistent formalism as far as I can tell. So let me describe each one of these pieces in turn. So this guy right here, the multiplication by some element of our field, is going to just multiply our input and get an output. So, for instance, if we just put in some kind of number up here, then we multiply by some other number, and we get another number as our output. So, the really nice thing that we can do that control theorists have figured out a long time ago is that we can take Laplace transforms and turn all those integrals into multiplication by 1 over s, where s is some variable that basically encodes the integration. And then we can take this, we can take our field to be the reals augmented by this variable s. And yeah. So this is going to give us basically one of those pieces that I was talking about, where I was pointing out the integration and the feedback. We're not going to deal with feedback just yet, we're just dealing with the integration here. So the next thing we can do, another piece of our formalism, is the addition. We can take two numbers that are inputs and we can add them together and get an output. So again, if you looked at the tutorial on Monday and Tuesday, we've got the opposite colors as what Sowiński has. So okay, so we've got the addition. We also have duplication, and we can always duplicate since we are in the classical case, so we don't have to worry about any kind of quantum stuff going on. And this just takes anything that we put in and gives us two copies of that anything. We also have 0, so anything that we're starting off with the zero-dimensional vector space and sending it to 0 in the one-dimensional vector space. And we also can delete anything. So we're starting off with anything in one-dimensional vector space, and we're just tossing it. And those 5 pieces are basically what are going to give us the category finvect, which is the free symmetric monoidal category on bicommutative bimonoids over the field K. So basically what that means is we've got a bunch of relations that these generators are going to satisfy. And something that as sort of kind of a side note is that Simon Wasley and Nick Woods also showed that we can weaken this thing from a field K to any commutative semi-ring rig K. So if we look at what relations this tells us, here's what we get. We get that we've got a commutative monoid, so the block structures give us the commutative monoid. We've got 0 plus anything is that anything that we started with, so it's just going to give us the identity morphism there. We've got the associativity and the commutativity, so things that we would like with commutative monoids. We can also flip everything upside down and turn everything the opposite color, so bizarro as and we get a co-commutative comonoid with the like morphisms. So we've got the duplication, and then we toss one, and so we end up with exactly where we started. We didn't do anything at all. So that's the identity. We've got the co-associativity and the co-commutativity. We also got the bimonoid relations, so I think we've become fairly familiar with these by now. And we've also got the root structure from the field can be recovered from these morphisms. So for instance, if we take some input and multiply it by b plus c, it's going to be the same as if we duplicate that input, multiply one of those copies by b, the other copy by c, and then add those two outputs together. That's going to give us the exact same value. And similarly, if we multiply by b times c, we get the same thing as if we multiply by c, then multiply by b. And multiplying by 1 does nothing, and multiplying by 0 does this weird break in our thing here. So it takes anything, gets rid of it, and then gives us 0. And finally, we've got the scalar multiplication is going to commute with each of the generators that we've seen so far. So we've got the scalar multiplication can just slide through the addition. It can slide past the 0 and just disappear. It can slide through the duplication, and it can slide past the deletion and disappear. Okay, so linear maps, they're really nice. They give us some really cool stuff, but they only give us signal flow in one direction. And that, like I said, doesn't tell us anything about feedback. So we need something a little bit more to get feedback into the picture. And that's going to be linear relations. So the linear relations are going to be these maps that are from the vector space U to V, and I'm representing them with the slashed arrow here. So whenever you see a slashed arrow, that's going to be a linear relation as opposed to just regular arrow as a linear map. So basically, I think we saw something like this before, where we had the existential quantifier and the that gave us so we can always do that when we have a Malchev category, and so that was kind of cool. Same thing is happening here. So, and we also can look at our linear maps and turn them into linear relations by just taking the graph of our linear map. So we have map from U to phi of U, then we can just take the graph U phi of U as our subspace of the direct sum of these two vector spaces. So we can see the composition of linear maps is just a composition of linear relations in a special way. And so we've got a second category to Erbele over with finite dimensional vector spaces over field K. That's going to include finvect as a subcategory. And it's going to be symmetrical monoidal using the exact same monoidal product as direct sum. And fully general signal flow diagrams are going to be the pictures of morphisms in Finrel. So we've got the generators that we saw before. We've got two more generators that we need in order to come up with the category Finrel. And John Baez and I showed that these two that we need to add in are the cup and the cap. So they're linear relations from the two-dimensional vector space to the zero-dimensional vector space and vice versa. And they just send a signal going the opposite direction. So whatever we have in one of these is going to match exactly what we have in the other one. And that's going to happen with both the cup and with the cap. So if we take the category of finite dimensional vector spaces with over K as the objects with linear relations morphisms, we can use the direct sum as our monoidal product, and that gives us a finrow and the word field K. And if we look at these morphisms right here, we can generate finrow with, of course, we also need to say what the relations are, just like we talked about the relations for finvect. So the relations that we get basically boil down to finrel is the free symmetric monoidal category on a pair of interacting bimonoids over the field K. And again, I'll expand this to a list of what those relations actually say. So we've got the 18 relations that we already saw, plus a few more. We've got the zigzag relations, which basically make this a dagger compact category, which is really nice. And so, for instance, we can turn around our morphisms and flip them upside down. And that, for instance, we've got co-addition is going to be addition going up instead of going down. And we have the co-versions of all of the morphisms that we looked at. So we have co-deletion, we've got co-duplication, we've got co-zero, and we've got the co-version of scalar multiplication. Well, scalar multiplication in the sense of multiplication by elements of our field. And so that automatically gives us reverse versions of the 18 relations that we started with. But we also get Frobenius relations on the dark structures, so we've got the familiar Frobenius laws here, and on the light structures. And we also have that these Frobenius structures are special, and we've got these extra, what Socians call the bone relations. And so they basically say that if we have 0 followed by co-zero, we get nothing. Or if we have co-deletion followed by deletion, we get absolutely nothing. We can also express the cap and the cup in terms of the other morphisms that we've seen so far. So the cap can be expressed in terms of the duplication and the co-deletion. And we already saw in Paul's tutorial that this is one of basically he was taking these as elementary and defining the cap like that. And he also defined another cap with the dark structures. And it turns out that these the dark structure version and the light structure version end up being related to each other by being a multiple of -1 on one of these wires. So for instance, you can see right here, if we have this input and this input, they're basically, you multiply one of the inputs by -1 and say that that's going to be the same thing as the other input. And that's exactly what happens here. We add two inputs together and then declare to be 0. It's got to be that those two inputs have the opposite sign if we're in some kind of field. We also have the reciprocal of multiplication by any element of our field is exactly the adjoint of scalar multiplication. So if we flip the multiplication upside down, it ends up being exactly the same thing as multiplication by the reciprocal. And that's basically what allowed, if you think about the antipode in Kilczynski's talk, that was basically what allowed him to say that he could flip it around and it didn't change the antipode. So that's one way of thinking about that. So this list of relations, this is the last one. So it was independently discovered about the same time by Bonci, Kilczynski, and Zanassi. And they also noticed that the Frobenius relations really can be thought of as coming from the interaction between the bimonoids, the structures that we have over the field K. And so that was kind of cool. So we've got the categories finvect and finrow. They're very nice. They're lurking within the heart of control theory, and there are a lot of other things that we have left left to discover, and this is just kind of the tip of the iceberg. And it'd be so. One of the things that is kind of I'm kind of excited about is being able to see maybe if we can put the idea of scalars in the quantum sense into these diagrams, where they don't really make sense just yet. Anyway, that's some future work. Yeah, thank you.
Anyone want to ask some questions?
I've got a question. So if you've got some, suppose you've got some complex behavior you want to produce and you want to use these ideas as a toolkit. So you design some huge control, some huge network with some complicated signal flow network. How do you know it's going to do what you want to do? You could just build it and see what happens, but is there some way that this formalism lets you simulate or execute or run a signal flow network?
So we can translate any sort of system of behaviors into a signal flow graph, and then we can do that translation in both directions, and we can see that the relation that we want, and we can turn that into some kind of signal flow graph, signal flow diagram, and then we can also take any given signal flow diagram and figure out what relation that actually describes. Is that kind of what
Yeah, I suppose so.
I think one thing that's good to note is that the big fat textbooks on control theory full of using
Yes.
signal flow diagrams to do things. So they were actually the ones that really
Yeah, so
know the full answer to your question. I could say more about it, but there's definitely technical knowledge there.
So this is more a remark to Jamie's question. So in the work of Jan Whitson and Henning Skilsson and myself, we have worked on this in percussion festival from last year. So the signal flow diagrams can also be expressed in terms of behavioral differential equations in the style of Jan Whitson. And in that way you get a co-advise semantics with it. So that might, I don't know, something along those lines.
Okay.
If I have some diagram, is there an easy way to tell when the relation it represents is actually a function?
you can tell if the relation is a function automatically if it has only the pieces that come from the first part.
Okay.
So beyond that, it might not be as easy to tell. I know that there are functions that do include feedback. So, for instance, the signal flow diagram that I put on the very first slide is something that is functional in nature, and it has feedback all over the place. So it would be a little bit more difficult to determine whether that's going to be a function rather than just a relation, just from looking at the picture. We can certainly do manipulations. We can convert it back into the algebraic and the system of differential equations description, and we could tell from there. But that's kind of so it's possible.
Yeah. So you were talking about linear relations over some vector space K. Could you remind me again why I'm supposed to think of integration as multiplication of some field K?
Right. So we so the control theorists have come up with a way to do that basically by taking the Laplace transform. And we could also, of course, take a Fourier transform and it would be basically do the same kind of thing. It's so we're taking the Laplace transform, and that's going to convert integration to multiplication by 1 over s. And so we're taking, that's how we're getting the field to be extended by S to give us integration as well. And so as sort of a scalar multiplication kind of thing.
So I think, so the point is if your function is e to the sx, and then you integrate it, it's the same as multiplying by 1 over s.
So,
Yes.
yeah.
Yeah, sure.
Yeah. Basically, yeah, just how the Laplace transform works, right?
Okay. Sorry, it's been a while. I
Yeah.
must have missed
So, yeah.
that day in school when we did that.
Any further questions? Then REL is an allegory, so there is the calculus of relations that you can also use to manipulate things.
It is an allegory, yeah.
Yeah. And you could show that using your string diagrams. But calculus of relations is maybe a bit different.
I have not looked at that closely enough to be able to give you a kind of definitive answer.
One interesting thing is that you can talk about one relation implying another, so it's not just a category, it's a category, it's coset enriched,
Yeah,
and that's one of the things that's big for them. And but control theorists don't ever seem to talk about that too much. Like this, that would be like saying that everything that's an acceptable behavior for this machine is automatically an acceptable behavior for some other machine. If this subspace is a subspace of that one. And they don't seem to think about that. We might try to think about that.
But this could answer Jamie's question. I mean, in computer science, you often have a relation and you want to implement it by a function. I mean, this is what some people use allegories for in computer science. So that you refine this requirement into an actual
It's interesting. Yeah, I don't know how people use allegories in computer science, so I guess I should.
That would be interesting line for research.
Okay, if no one has any more questions, let's then chase it for time.